This is the agenda. So we'll start by a quick overview of the MIPI D-PHY and C-PHY. We'll talk about the additional block that the C-PHY needs and uses. We'll talk about a comparison between the D-PHY and C-PHY in terms of the trade-offs. Then we'll introduce the dual mode D-PHY, C-PHY combo IP. We'll talk about the transmit and receive, talk about use cases, adoption, challenges, and conclusions, and then we open it for questions and answers. So this is just a quick overview of the history of the D-PHY. The D-PHY started in 2009 at 1 gig, and every couple of years there was increased data rate, additional features. In 2011 it was 1.5 gig, for 2014 2.5 gig, 2016 4.5 gig, and this year there was an update on some of the features. So that's the D-PHY. This is the block diagram of the D-PHY. So D-PHY is source synchronous SerDes. So you have a clock and so many data lanes. It can be one or more. This is the block diagram of one lane. So the D-PHY, as many of you might know, has multiple modes of operation, high-speed operation, low-power operation. So you end up having a high-speed TX, a low-speed TX, high-speed RX, low-speed RX, as well as the contention detector, since this is a bidirectional operation. Then, of course, you have the serializer, deserializer, and the state machine to enable you to transition between the different modes of operation. This is the waveforms, the timing diagram for the D-PHY. I'm going to cover that with the C-PHY in a subsequent slide. This is C-PHY was first introduced in 2014, running at 2.5 gig symbol per second. In 2016, it went to 2.8, and version 1.2 in 2017 is running at 3.5 gig symbol per second. And for the D-PHY, one symbol is 2.28 bits. This is the block diagram of the D-PHY. Basically, the D-PHY sits on top or shares a lot of the functionality with D-PHY. So it uses the same low power operation. And you also, of course, have the high-speed operation and the contention detector. Of course, many unique things about the C-PHY. So each lane is a trio, 3 signals. Of course, so 3 signals go from the transmitter to the receiver. Additional, of course, you need the serializer, deserializer. There are 2 additional functions that the C-PHY needs, which is the encoder and a mapper, and we'll talk about that in the following slides. So this slide shows the timing diagram for both the D-PHY and the C-PHY, very similar. As I mentioned, the low power operation is almost identical. The difference is in the high speed operation, because of course this is like binary bits and this is symbols. So you have a preamble, a sync, a postamble, but very similar structure, as you can see. Now we're talking about the unique features of the C-PHY. So I guess the first thing you want to know is that you get more than 1 bit per symbol. You get 2.28. So you are able to run at a higher data rate at the same transition rate. You are able to share the same pins with the D-PHY. So you're using the same pins, the same balls, the same transmission line. You get flexibility in the C-PHY because the clock is embedded, which means that each lane is independent. Of course, big advantage is it does coexist with the D-PHY, so you are able to transition between the two or use the same IP as the subsystem for both. Because you have more than one bit per symbol, you have the opportunity to save power because you are running at lower transition rates. In terms of the flexibility, we did talk about the embedded clock, which enables you to assign any lane to any AP link, which of course doesn't happen in the D-PHY because the D-PHY, each data lane is assigned to, has to work very closely and tied to a clock, the clock lane. You are eliminating the clock, which of course eliminates the interference coming from a single frequency clock. Because of the nature of the C-PHY, you have some unused codes that you are can be used for additional functions, such as the alternate low power mode, fast bus turnaround, low latency, and of course, because you have a lower data rate, the design of the board and things like that can be less complicated in some ways that lower the cost. This is a couple of slides courtesy of Qualcomm, and it basically shows kind of the big picture of the C-PHY. So if we start here, you see, of course, each lane is 3 signals, and you can have 1 or 2 or 3 lanes. In terms of the layering, you have the protocol, of course, on the top. You have the serializer, and you have the channel. What you have additionally here is the mapper, which goes from 16 bits to 7 symbols, and the encoding function, I should say, the mapping and encoding. Okay, here on this side, that kind of summarizes the high-level operation. So on the transmitter side, you have 3 signals, and this is now not binary signal. This is 3-level signals. So you can have high, you can have low, and you can have mid-range. So actually, this is high, this is low, and this is mid-range. And on the receiver side, you are looking at 2 of those 3 signals at a time. So A, B, C. On the receiver side, you have A minus B, B minus C, and C minus A. So on the transmitter side, that's how it would look like. In terms of the receiver side, you're looking at the difference, so that's how it looks like. And maybe I can talk a little bit about why the encoder is needed. So the encoder does many functions. Among them is it ensures that you have at least 1 transition per symbol. So the embedded clock is there, enables you to, without complicated CDR, extract a clock. You are guaranteed that you have 1 clock per symbol. So that's helpful. Another thing that the encoder does is to make sure that the input to each one of the differential receivers is non-zero. Of course, you cannot allow that to happen. And then another third function is it ensures that the common mode voltage of the 3 signal is constant at the mid-range. So basically, you have 3 signals here that allow you 8 combinations. Some of those combinations are not allowed because of what we talked about. There is some restrictions. And when you look at it, you end up with 6 wire states that are allowed because of the fact that you are trying to ensure there is always 1 transition per symbol. Then if you're looking at 6 states, you cannot stay at the same state from one UI to the other, which means that you always have to be transitioning, which translates into 5 possible transitions between the 6 states. So that means that you really have 5 possible transitions. And you can think of that for a binary, you have 2 options, 0 or 1. For this system, now we have 5 different options. So that translates into theoretically maximum of log 5 base of 2, which is 2.3219 bits per symbol. You can think for a PAM4, you have 2 bits per symbol. Log 4 is 2, PAM8, log 8 is 4. In this case, it's log 5, which gives you the theoretical limit. Now, in terms of what we really end up using is 2.28 because you're really going from 16 digital bits to 7 symbol. So that gives you that ratio. Now, why 7? Why 7 symbols? Where does that come from? So this is where the mapper comes in. So you have a mapper that maps the binary to the C-PHY signals that the C-PHY can understand. And you go from the input, at the input of the mapper, you have 2 to the 16 states. And at the output of the mapper, you have to have the same number or larger number to be able to map it. Otherwise, the thing wouldn't work, right? So basically, 5 to the power of whatever the number of symbols have to be larger than 2 to the 16. So 5 to 6 would give you less, 5 to 7 give you more, and that's how you end up using 7 symbols. So that allows you for some extra unused symbols, and those are the ones that we were talking about earlier, that we said is actually not wasted. It's used for other uses, such as synchronization, link control, event signaling, low power data transmission, run length limiting. So that's kind of a distinction between the C-PHY and the D-PHY in the sense that the D-PHY uses the token, for example, which is a valid data in the C-PHY because you have those additional codes that are not allowed. You can use them for those kind of functions. One interesting feature of the C-PHY is that although it's multi-amplitude system, on the receiver side, you are really not looking at the multi-amplitude information. You are only looking at zeros and ones again. I mean, it's a differential input. You are looking at the difference between the two. You are not trying to detect the difference between the high and the mid, for example. So that, of course, simplifies the receiver. Basically, you end up using the same kind of receiver that's using for the D-PHY. Here, we are comparing the D-PHY to the C-PHY. So in terms of the design, the C-PHY is definitely a more complex system, IP, subsystem. The D-PHY is source synchronous. You're sending the clock and the data. So on the receiver side, you're very easily using the clock to sample. Sometimes you're deskewing. The C-PHY has more complex CDR, but you are ensured that you always have one transition per symbol, at least one transition, so that certainly make it simplified compared to a complex CDR. In terms of the power per gigabit per second, you have an opportunity to save on the C-PHY because, of course, you are running at multiple bits per symbol. In terms of the area, the D-PHY is compact, smaller area, because it's smaller area because you don't have the additional blocks, right? But then if you look at the area in terms per gigabit per second, then the C-PHY have opportunity to save some area when you measure it that way. In terms of the total bandwidth that the C-PHY allows you compared to the D-PHY, the C-PHY has some advantage there, again, because of the higher transmission density. In terms of the minimum configuration for the D-PHY is 4 pins, 1 clock lane, 1 data lane. For the C-PHY, it's three pins. In terms of flexibility, the C-PHY, as we mentioned, has some additional flexibility in terms of having each lane totally independent. Transmission efficiency, C-PHY has some advantage there because it's 2.28 bits per symbol. Testing for both the D-PHY and C-PHY are complex compared to other standards because of the use of both the low power operation and the high speed operation. But of course, the C-PHY have even more complex requirement because you're looking at 3 signals as opposed to differential, which is very different. Yeah. In terms of the adoption, of course, the D-PHY is a much more mature IP. It has been around for a long time. It has been very widely adopted. The C-PHY is a newer addition. It is seeing accelerating adoption in some areas, and the good thing is they do coexist. This slide shows the saving that you can achieve with the C-PHY. So if you start with the same total bandwidth and translate it into the C-PHY, how it would work, and the D-PHY, how it would work, you would see that for the C-PHY, you can use 2 lanes, each one running at 0.875. For the D-PHY, it translates into 4 lanes, each one running at 1 gigabit per second, which means that here the toggle rate is 12.5% lower for the C-PHY, and the number of bits is reduced by 40%, because then here you have 6 versus the 10 here. Yeah. So now let's talk about the dual mode IP that we have silicon proved. Of course, it's sharing the serial interface pin. Depending on the implementation, we have been able to share all of the D-PHY blocks is reused for the C-PHY. Of course, to minimize the area. The power per gigabit per second is achieved with the C-PHY. We enable a smooth transition between the D-PHY and the C-PHY. And of course, you gain the benefits of the power performance area that the C-PHY provided, while maintaining the compatibility of the D-PHY. So really, you only use those when you need to. This slide shows a block diagram of the combo IP. So you can see all the darker orange blocks are the ones that are shared between the D-PHY and the C-PHY, which is the vast majority of the blocks. So no D-PHY block is unused for the C-PHY. Of course, as we mentioned, for the C-PHY, you have additional blocks, such as the mapper, demapper, and encoder, decoder, and also the CDR. This slide shows the coverage that both Qualcomm and Mixel have today. So the IP by both companies have been silicon proven in 3 different foundries and in 7 different nodes, starting at 65, 55, 40, 28, 14, 10, and 7. Some of those are Mixel IP, and some of them are Qualcomm. And the key here shows what has been silicon proven and what has been taped out, and we haven't seen pre-silicon, basically. Okay, and with that, I'd like to turn it over to CK, and he will walk us through the silicon results from both companies and also other companies.
Thank you, Ashraf.
Sure.
Hi, my name is CK. My name is CK from Qualcomm. I think I heard one question from someone while the SK-CHY is presenting. What was the technical challenge when we have a C and D-PHY combo? I can answer for that. I think, yeah. So in the design side, maybe there's some challenge to have the both design in compact, but the challenge is more on silicon validation, more on PCB design side, actually. So like you say, one is differential and the other one is, it's a pseudo differential. I don't want to say it's a fully single-ended, but it's a differential because the return current is coming back, but it's a pseudo differential. So, but 2 and 3 is common denominator. It's hard to find it. So when you design it, you have to design all the signal line like a single-ended way. So not tightly coupled, loosely coupled is a strongly recommend. So we've been seeing that in the differential, usually you go with the 2 differential line very tightly coupled. But in the C-PHY case, there's another signal next to it. If that is combo with the other differential, then it's not tightly coupled together, then 3 signal is not properly matched. It could create additional skew in the testing. So that was the challenge area. You often mistake, then you will see some problem. And the low speed is okay, but high speed, that has to be carefully designed. So this is the silicon test in the actually Mixel side and Qualcomm side. We use both the key-side oscilloscope and the setup. So usually it's a combo, but practically speaking, we do design TX and RX separately because TX is oriented, targeting to display, and then RX is mostly camera interface. So the thing that I'm going to show you guys is actually separate. One is in the TX, the other one is in the RX side. In the TX side, it's easy to test it. I would say you are just monitoring what is coming out from the silicon. So basically, it has some RTB board, termination board, and some setup here, and you can see the waveform from the device. So again, all the logical part is common to both NCSI, DSI. We both use DSI-1 or DSI-2, CSI-1 and 2 as a protocol layer. Only difference is physical side. So physical side test is most important thing. So this is set up, and then this is silicon result from Mixel design. I think they're still more optimizing it. So, but it was quite successful to up to 2.5 gigabps. I'm sorry, 2.5 giga symbol per second. So symbol per second. So that means we use different terminology, right? It's because C-PHY can send more bits than the symbol time. It's 2.28. Don't forget. So it's 2.5 giga symbol per second means 2.5 times 2.28, which is 5.7 gigabps, equivalent to the D-PHY. So message here is this design is a bit C and D-PHY, and then they don't hurt each other, and we can achieve the same performance, maximum, spec performance. So, and this is our Qualcomm result. So we also see we check the up to 2.5 gigabps also, and then MIPI D-PHY and C-PHY has different speed target for different channel characteristic. So in our test, we also cover short channel and the long channel too. And this is another contributor. I'd like to give my thanks to this company called Sony. Sony is also actively participating in TX design. So Sony is also showing that the combo PHY can achieve actually more than what we can do. It's actually 3.5 gig. And then as standard channel, the 3.5 gigabps is already achieved. And then short channel, which is mostly the mobile application, we already achieved 6.5 gigasymbol per second. And of course, it's a combo PHY, so we also check make sure D-PHY functionality or D-PHY electrical characteristic has been also validated. Yeah, this is also TX. We actually use the same TX design, so it doesn't add extra capacitance. Of course, there's a little more, some trick is required, but the message here is the same drive can be used for both C-PHY and D-PHY. So if you have two different drivers, they will add more capacitance, so it will hurt each other, but it's a combo. So same driver, the same receiver is being used. And for the RX side, RX is right now, we cannot see the received signal. So it's maybe post-processed signal. So RX side, we go with two different ways. One is we check the electrical timing margin, electrical sensitivity through the logical test. So test setup is very similar, but for RX side, the test pattern is driven by the one of the test machine called the AWG. So the three signal signaling is driven by this machine, and then the receiver is taking it and process it and check the electrical timing parameter based on the go-no-go test. And then another test is also the image transfer. So this is a fixed image case and some uncalibrated camera image we are seeing here. So some bar pattern and uncalibrated camera image and cathode image. And then we also use another test box in this test. This test is mainly focused on the link operation. So another test box on the top, I don't know, is being used. And then, of course, on the RX side, actually, what we see is what we captured. So we had an emulation tester set up. So in this test, Sony and OmniVision has contributed their. We work with the Sony and OmniVision to make sure the both C-PHY and D-PHY function can be smoothly brought up. So Sony camera sensor and OmniVision sensor was attached to our RX device, and then it was brought up through the emulation platform. And for the display side, sorry about this lousy connectivity, but we work with a couple of display company, so I make sure also. I mean, D-PHY is well validated through many years. So our main focus for this silicon test was a C-PHY, combo design and C-PHY using C-PHY signaling. So this is one of the company, and then the resolution was, I don't know, this resolution is maybe QHD. So you have some image here and there. I used to have a beautiful Spider-Man, but my company is not allowing to show. So I override this general image. And then we do some PPA analysis. So and TX and RX side. So again, this is combo PHY. Combo PHY, because of combo PHY, so there is some area waste. It's not waste, but area addition. But it has many advantage, because first of all, we can cover very wide range of resolution, and from low to all the way to the top. So the C-PHY is actually thanks to the encoding efficiency. So even the same toggle rate, let's say 3.5 giga, but it can support more than the higher resolution camera. For example, here, these days 16 megapixel, 120 frame per second. That does require 24 gigabps. But as of today, in order to do that lane speed has to be 5.76 gigabps for D-PHY case, and it's not available. But we can go with 3.37 gigasymbol per second for C-PHY because of the encoding, which is available. So that's one of the advantages. And the area, again, increment is depending on application, but my experiences say it's usually less than 10%. And then initial version takes about 10%, but when you move to the next generation, you can reduce furthermore the gap. And then again, the message here is again the very wide range of resolution can be supported by having C-PHY and D-PHY combo. And then for C-PHY mode, also even, let's say, even same resolution, C-PHY can be run at the lower toggle rate thanks to the encoding. What that means is the most power consumption in the design is analog front end. So in the analog front end, you can use a lower bias current, and then you can take advantage of this encoding ratio, encoding efficiency. So yeah, if you see that this table is very lousy, but the message here is the overall by having combo PHY, I mean there is more benefit than the area increment. And as of today, for the camera and display, the Sony and the OmniVision and few others are adapting this C-PHY technology. And then also their design have a combo PHY as far as I know. And display side also, I haven't got the permission to share the name, but we work with most the major DDIC companies, so they completed the IoT test. And the IP side, we have a good Mixel design. And the AP side, we know that Qualcomm has the solution, and then some others. And test side, the key side, Tektronix, Introspect, and Moving Pixel company has test solution. And then we also, the common mode filters from the Murata and Panasonic and TDK is the common mode filter solution. So it's spreading out, it's widely adopted, and I hope, so it's a non and Silicon Valley technology, I say.
Thank you.
I'll give this to Ashraf again.
Okay, we are running a little bit late, so I'll try to speed up. So CK talked about the challenges. There are certainly challenges to the C-PHY. As we mentioned, the CDR is not trivial and need to be programmed based on the data rate. You have multi-level signaling, which makes things a little bit more complicated. On the other hand, the receiver is differential, so it's not looking at the difference between the levels, it's just high and low. And of course, you have some challenges on the PCB design as CK discussed. So in conclusion, the C-PHY is a very powerful but complex IP subsystem, right? So that's the price you pay is the complexity. You pay a little bit of price in terms of the area, but then you get the benefit of the power reduction and the efficiency. And of course, the combo D-PHY, C-PHY is even more complex than just a C-PHY and even more powerful. So the C-PHY provides a power performance area improvement at the expense of that complexity. With the combo PHY, you get a lot of flexibility, being able to use it as a C-PHY or D-PHY, and using the enhancement you get with the PPA. It's a good thing that it is possible to reuse all the D-PHY blocks for the C-PHY functionality, so the area increase is minimized. We see good traction, as CK mentioned, with the adoption. Certainly, the sensor adoption is very good, and the display is also coming along. So we have the C-PHY, D-PHY combo silicon proven in multiple nodes, and we think that should help the ecosystem. Thank you. Unfortunately, we are running late, so no question and answers, but we would be glad to answer any questions offline.
Thanking Ashraf and CK.